If you guys remember before break, we dealt with these things called graphs. And if we recall, the person that we were concerned with before break was Euler. We talked about Euler paths and cycles, which essentially used every edge exactly once. Right, it was kind of a puzzle where we did the bridge problems on Wednesday before we went to break, and we were concerned with whether or not you could go over every bridge. You could travel around the city, going over every bridge exactly once, and either ending up back where you started or ending in a different location. Either way, we had some nice theorems for knowing whether or not these Euler paths and cycles existed. Next thing we're going to look at is this thing called a Hamiltonian circuit. So let's go ahead and define that. So today's focus is on Hamiltonian circuits, which the word circuit essentially acts kind of like the word cycle did, where a Hamiltonian circuit, because it's called a circuit, will start and end at the same vertex. And the main difference between an Euler cycle and a Hamiltonian circuit is that Hamilton or Hamiltonian circuits are concerned with visiting every vertex exactly once. So this Hamiltonian circuit will visit every vertex exactly once. The most common kind of example of this that you'll see in textbooks or examples online has to do with the traveling salesman problem. That's what the problem is called, because it describes some kind of salesman that has to travel around to different cities or states to sell something. And so it doesn't make sense for this traveling salesman to visit a city more than once. So the job is, or the problem is, to find the cheapest route that the salesman can take while visiting all of the cities that he's supposed to visit on this trip, right? So if he's supposed to go to 5 or 6 cities, and you'll see an example of kind of exactly that in the handout that we have today. It's not necessarily a traveling salesman, but it is a person who owns a business in, it says New York City. She needs to fly to Los Angeles, Chicago, Miami, Seattle, and Houston for a business trip before flying back home. So our starting city and ending city is set, and we are asked to find a kind of a path for this person, and the order in which she visits the cities does not matter, but the flight prices kind of determine which flights you'll take, and you're wanting to make a Hamiltonian circuit because you don't want to visit, for example, you don't want to visit Miami more than once along this trip, right? You want to go from NYC to somewhere, and then travel around to all of these cities, and then end up back in New York City. And what we're mostly concerned with Hamiltonian circuits is not the whether or not there is a Hamiltonian circuit, because in like this example of the traveling business person, there's always going to be flights from every city to every city that we're looking at in these questions. So there's always going to be a Hamiltonian circuit. We're more concerned with taking the cheapest flights, or using the we call them the least weighted edges to traverse in this Hamiltonian circuit manner. So let me make a note of that. We're not concerned with existence, we don't really ask the question of, is there Hamiltonian circuit on this graph or is there not? Mainly because there's no nice theorem for saying whether there is or isn't a Hamiltonian circuit. We're more concerned with the cheapest or lowest weight circuit we can find. So we're concerned with finding the cheapest, also called the lowest weight circuit. Right, that's going to be the task for whenever you see Hamiltonian, you're going to be applying either the, well, I guess we're just applying the, there are a couple of algorithms. Yeah, we're doing the, we have a couple of algorithms for finding this cheapest or lowest weight circuit. So let's talk about these algorithms, and I'll draw up an example here so we can use the same example for doing a couple of these algorithms. So we'll draw a graph with 4 vertices. We'll call them A, B, C, and D. And we'll have some edges here. We'll have A, B, B, C, C, D, and D, A. We will also have the path, or the edge, AC, and the path DB. Right? As well as being given a graph to work with, we also need to have these weights that we're trying to minimize. So each of these edges will be, you can kind of keep the flight from city to city example in the back of your head while we're talking about this. When I put weights on these edges, like AB is going to have a weight of 6, BC is going to have a weight of 3, CD is 9, AD is 4, AC is 7, and the edge BD is going to have a weight of 10. These numbers are not something that you can figure out from looking at the graph. These weights will be given to you in some way. You can think of these as kind of like the cost of a flight from one city to another, or like how much gas you use to drive from one place to another. These are going to be kind of costs for using those edges. So if I'm going to start at a vertex A and travel around this this graph, and I'm concerned I want to visit every vertex exactly once, I could go A to B to C to D and back to A, but there will be a total cost associated with that. So going from A to B would cost 6, and then a 3, and then a 9, and then a 4. So we would add those up. So if I use those edges to travel around, I would get a total of 10 and then 22. So total cost would be 22 if I went that way around. Instead, if I were to do something like go from A to D, and then D around this edge to B, and then to C, and then to A, that would have a different cost associated with it, right? I would go 4, and then 10, that's 14, and then 3 more, that's 17. We would take 7 more, that would be 24. So that one is more expensive to travel around that way, even though we're traveling to every city or every vertex exactly once. So the concern is going to be with finding the cheapest such circuit. There's a few more that we could come up with, right? I could go A to C, and then I could go to D that way, and then travel around and get back to A that way. So that would be a different Hamiltonian circuit. So the concern isn't with whether or not there is a Hamiltonian circuit, it's with finding the cheapest one. So let's talk about the few different algorithms that we're going to use here. We're going to use, first one we're going to talk about is the nearest neighbor algorithm. For the nearest neighbor algorithm, to be able to use it, you must be given a starting vertex. So the question has to say something like, use the nearest neighbor algorithm starting at vertex B or starting at vertex A, and use the algorithm from there. How the algorithm works is you start at the given vertex, whatever the question says. You're going to choose the edge or travel along the cheapest edge possible to another vertex. Right, so you start at a specific vertex that the question gives you, and then you just pick the cheapest edge that you can take from that vertex, which means in the example of the business person, they would just take the cheapest flight to one of the cities that they want to go to. And then the nearest neighbor algorithm, just the last step is to continue until every vertex is visited. Exactly once. And return home. For example, if we use this graph given to us, and we want to start at vertex B and use nearest neighbor algorithm, we would start at vertex B. So the answer, how we would write the answer to this is we would start at B, and we would write the edges that we take. We would write the next vertex that we would visit along this path. So if I'm starting at vertex B, what's the cheapest edge, or what's the cheapest edge I can travel along from vertex B? C. Good. So we're going to go from B to C. That's going to be our first travel. So we're going to go from B to C. And then from C, what's the cheapest edge we can take? Now keep in mind, we don't want to go back to B yet because we have already visited B. We don't want to go back to B until we're done with everything. So the next one to take would be, yes, we want to go to A. So we would go from C to A. And then from A, you kind of run out of options with such a small graph because we don't want to go back to B yet, right? We don't want to go back to C either. We've been to C, and we're currently at A. So the only option really we have here is going to be to go to D next. And then since we've now visited every vertex in this graph, we need to return back to B. So the only way we return back to B from D is going to be this outside edge to get back to B. And we will have a total costs associated with this, or total weight. Let's say weight. Associated with this kind of pathing. And that's just going to be adding the weights of the edges that we visited along the way, or that we traveled along the way. And that's going to be 24. So you add these together. You can keep track of them on this list of edges that you travel along. So from B to C, that was a 3 cost edge. We took a 7, we took a 4, and then we took this last edge that was weighted 10. So you add those up and you get your 24. Right, so there's an example using the nearest neighbor algorithm. So I said that the nearest neighbor algorithm, to be able to use it, the question has to tell you which vertex to start at. Because if you can imagine, if we start at a different vertex, the cheapest edge we can take might be different, or we might never take this 7. For example, if we start at vertex D, the cheapest edge we can take would be this DA, which would be a weight of 4. And then from A, the cheapest edge we can take would be this 6. And then from there, the cheapest edge to take would be the 3. And then finally, we would have to return home. So if we were to do the same thing, the same question, starting at vertex D, we would travel D to A to B to C to D, which would give us a different Hamiltonian circuit and a different total weight. Now, the nearest neighbor algorithm has to give you a starting vertex, but if we now talk about the repetitive nearest neighbor algorithm, so the repetitive nearest neighbor algorithm will not give you a starting edge because, or a starting vertex, because we're going to perform the nearest neighbor algorithm starting at each vertex. So we already did the example where it said to start at B, but if the question instead said to do the repetitive nearest neighbor algorithm, we would do the nearest neighbor algorithm starting at A, and then we would do it again starting at B, do it again starting at C, and do it again starting at D, and then choose the Hamiltonian circuit with the lowest total weight. Right? When I just talked about starting at D, we saw that we would go D to A to B to C to back to D. That has a total weight of 22. So when we do that, we see that that's actually a better version of this previous Hamiltonian circuit, right? If we started at A, we might have a different total weight. If we start at C, we might have a different total weight. So you have to do all 4 starting vertices to see the total weights of all 4 possibilities and choose the cheapest one from there. So you would have 4 answers like this if you wanted to do the nearest neighbor algorithm, and then you would choose or box the one that had the lowest total weight, right? And that would be the cheapest Hamiltonian circuit we could find on this given graph. Right, so I'm not going to do that whole example, but I think the one I did starting at D is the cheapest one in this picture. I think you get the same one if you start at A, because you go A to D, and then this is the cheapest, and then this is the cheapest, and this is the cheapest. So sometimes you get the same Hamiltonian circuit starting at different vertices. If we started at C, we would go C to B, and then B to A to D, and then D to back to C. So you get the same thing. As long as you don't start at B, you get the same going around the box, which is the cheapest Hamiltonian circuit in that picture. Okay, that covers the everything that has to do with the nearest neighbor algorithm, whether it's the one vertex starting vertex given to you or the repetitive version where you have to do it for every vertex. Next, we want to talk about the cheapest edge algorithm. The cheapest edge algorithm, we start by listing every edge weight in ascending order. So we list all edge weights. I'm using the word weight and cost kind of interchangeably here. It's just going to be whatever the cost or the weight of each edge is. We're going to list all of them in ascending order. Meaning smallest to largest. And then we start creating this Hamiltonian circuit from this list of edge weights. So we will add the lowest weighted edge to the circuit. So we just start by picking the lowest edge and just blindly adding it to an edge that we're going to use, right? So if we're looking at this picture here, without having any kind of starting vertex, we look at the whole graph. First of all, we would list all of the edges, all of the weights. So it'd be like 3, 4, 6, 7, 9, and 10, right? Those are all of the edges on this graph. We're going to just take the smallest one and we're going to include it. So that's going to be one of the edges of our Hamiltonian circuit when we're done. Okay, so we add that to the circuit. And then to continue, we keep adding valid edges. And we'll talk about what valid is, or what's valid and what's not valid. We'll make a little underline on that one because we're going to define what valid edges means. We're going to keep adding valid edges until a Hamiltonian circuit is formed. So valid edges is kind of a heavy thing there. It has some built-in definition because we can't just randomly add all of the edges that we want to add. A valid edge means that the vertices of a valid edge are available. Now that word available also means something. And available, I'm going to describe that as being not flown. And the word flown there comes from like air flights, like flying to a city and then flying away from that city. So I'm going to draw a little picture here. If you have a vertex and you've used an edge that's going to that vertex, and then you've used an edge going out of that vertex, this vertex here is no longer available. I know it seems a little convoluted the way I've described this. I'm trying to be very precise about this definition. In practice, we're going to just add edges to our circuit as long as the two vertices that are at the endpoints of that edge have not already been used twice. So let me go back to this example here. Let me draw it again down here so we can look at it. We had a graph. We'll draw a smaller version of it, A, B, C, D, and we had all possible edges on this graph. And the weights were the 3 was here, the 4 was here, the 6, the 7, the 9, and the 10 was on the outside here. So we make a list. Let me start by making the list again. 3, 4, 6, 7, 9, and 10. as our list. And we're going to start by adding edges. Now, it makes more sense to do this on the graph itself and not write out like we did for this one. We had some kind of starting vertex to begin with, and then we went from there. But here we don't have a starting vertex to begin with. Also, as you're working through this and creating a circuit, your circuit doesn't have to remain connected the whole time either. So the first edge we check is the 3, and since we're just starting out, we can include the 3, the edge that has a weight of 3 in our Hamiltonian circuit. So I will add that edge to my circuit. Now comes the weird part about adding valid edges. Going down this list, we're going to consider each edge, and if it's valid, we're going to add it. If it's not valid, we're not going to add it to our circuit. So the next edge we have in question is this edge AD that has a weight of 4. Both A and D have not been used at all yet, so these are valid. This is a valid edge because the vertices are available. So I'm going to put a little check marks next to that 4, and we are going to add this 4 to our circuit. Now notice that my circuit so far is not even connected to itself. I have 2 pieces that are eventually going to connect to each other, but for now I have some kind of floating edges that I've added to my circuit. The next cheapest edge to consider is the 6. And when I go and look at the 6, that touches 2 vertices A and B. A and B have only been used once. We've only used one edge going to B, and we've only used one edge connecting to A, which means these 2 vertices are still available. So as soon as they're used twice, they become unavailable. So as soon as I say, okay, yes, I'm going to use this edge that has a weight of 6, A and B are now considered flown because there's we've used 2 edges that are touching A, and we've used 2 edges touching B. So now A and B are no longer available. So when I go look at edge with a weight of 7, now we're considering this one. While C is an available edge, A is not available to use. So we would say, nope, we're not going to use that 7 because that would add too many edges touching A. Right, if you remember, the whole idea of a Hamiltonian circuit was to visit every vertex exactly once, right? If I have these 2 edges here in my circuit, I'm going to go along one of these to visit A and leave from A using the other one. If I somehow had another edge that was going to it, that would be too many because we only want to visit and leave A once. So then the next edge along the list is the 9. And if I look at this edge that connects D and C, D hasn't been flown yet, and C also hasn't been flown yet. So 9 is a good edge to use. And we will include the 9. And as soon as you have a closed loop, as soon as you have some kind of circuit that visits every vertex exactly once, you stop. You don't even consider adding any more edges because you stop when you've formed a Hamiltonian circuit. Now, how do we write our answer? Part of the work you need to show for this is the list of weights and which edge you've included and which edge you've not included, as well as probably a drawing or like a highlighting or bolding the edges that you're using. And as for the answer here, if we were writing the answer that we just came up with, once we have our circuit, it doesn't matter which vertex we start at, as long as you travel around the vertices in this manner. We can start at A, for example, go to D, and then to C, and then to B, and then make sure you end up back at the vertex you started at. You don't have to start at A. You could start your circuit at C. It doesn't matter. What we're really concerned with is that the total weight is correct. Which in this case, if we go from A to D, that's the 4, and then the 9, and then the 3, and then the 6, which gives us a total weight of 22. So this also gives us the cheapest Hamiltonian circuit in this graph. Let me pause there so you can catch up and see if there are any questions from anyone. Yes. The question was, can I do the example on the worksheet? And I will help you with the first example, and then you can do the second example on your own. Any questions on any of the definitions or anything like that?
Professor?
Yeah.
If you continue the repeating nearest neighbor algorithm and some of the answers you're getting are like both A and B have like the same weight, how would you choose a winner like of what has the lowest weight if some of them
Good.
have the same weight?
Good question. The circuit itself is not just like defined by how you list these. It's kind of the picture, the path that you take is not defined by where you start and where you end. Like I said, when we found this one here for the cheapest edge algorithm, I just decided to write it by starting at A. I could also start at B. So getting multiple of the same. Oh, I guess you're asking if two different looking circuits have the same weight, then it doesn't really matter. You just give an example of the cheapest total weight pathing. Does that make sense? As long as you find a cheapest travel, whatever cheapest circuit, you could just give that cheapest circuit. You don't have to say like these are all the same or whatever. As long as you found a cheapest one, you're good.
So you basically would just give the number instead of like the letter.
I would give an example of a specific Hamiltonian circuit that gives you that weight. For example, in this one, it was this attached to this circuit. I could write it differently. I could say go from B to A to D to C back to B. It would still have the same weight. So give an example of a circuit that has that cheapest weight along with the weight.
Okay, that makes sense. Thank you.
You're welcome. Any other questions? Okay, let's go on and look at this example. There's a brief recap here. This gets very, very large. So let me think how we can make this smaller. So what happens is because they try to make this as realistic as possible when the examples are written. When you book flights, usually going from, for example, going from New York City to Miami will be $98, but then if you wanted to go from Miami back to New York City, that'll be a different price, right? So this introduces the idea of edges with one direction. So when we draw a graph for this, we would have to do something like, don't draw this yet, but we'd have to do something like if this is my New York City and this is my Miami vertex, we'd have to draw the edges where you travel one way for a certain price. So from New York City to Miami would be $98, but then Miami to New York City would be $286, right? So we'd have to include travel there and back as different edge weights. And then when we're trying to form our Hamiltonian circuit, we'd have to pay attention to which way the edge is going, and and that gets a little bit complicated. So I'm going to try to make this a little bit simpler and kind of remove that idea of like having different prices going there and coming back, because that's going to make your graph look ridiculous and also very hard to like figure out what the cheapest paths are going to be. What we're going to do instead is we're going to assume that traveling to and from the same two cities is going to cost the same. So going from Miami to New York is going to be the same as going from New York to Miami. So I'm going to get rid of a bunch of these costs. Essentially, we're going to... Do I need... we don't need anything below this diagonal. So you can cross out these return flights, and we'll just assume that going to a place and coming back from that place are going to cost the same. So we're going to use this triangle of weights here with a 1, 2, 3, 4, 5, 6, 6 vertex graph. Is still going to have a lot of edges, because if you count all of these, that's how many edges we're going to have. But it's going to be a little bit better than having twice as many edges on that graph. So let me start by drawing a graph for this. We're going to have 6 vertices. We'll kind of space them out nicely so that we can what's the best way to represent this? I guess as a hexagon would still be the best way. So we want to do 1, 2, 3, 4, 5, and 6. So we'll do something like that. We'll label these as, do they all have different starting letters? They do. So we'll call this one Chicago, Houston, LAX, Miami, New York, and Seattle. And as we're drawing edges, we'll put the numbers on them so that we're not getting confused. A flight between Chicago and Houston will be 305. A flight between Houston and LAX will be 324. I guess we should just go along these numbers. So we did this number. Let's keep track of this. We did this number. We did this number. This number represents LAX to Chicago. So we'll draw LA to Chicago as a flight, and that'll be 314. Next number, the 244, is going to be between Miami and Chicago, so we'll draw that one as well. That's 244. Between Miami and Houston is 214. Between Miami and LAX is the 514. That one's good. And then it's going to get a little bit more crowded as we go. 204 is New York City to Chicago. So this one here is 204. Try to keep the numbers close to the edges that you're drawing, because as this gets busier and busier, it'll be harder to identify the numbers. 336 is from New York to Houston, so N to H is going to be 336. 177 New York to LAX. It's 177 there. 98 connects New York to Miami. That's 98. And then we got to do all of the Seattle connections. So Seattle and Chicago, That's 179. Seattle and Houston. Try to find a path to get there. That one is 319. Seattle and LAX connection. Going straight across, that's 242. Seattle and Miami, which we'll draw in there, is, I guess you could draw it on the outside as well. I don't know why I tried to put everything in the middle here. That's 307. And then finally, Seattle to New York is the last one, which is 169. Okay, so that's all of the flights. Imagine trying to put to and from flights for each of these. It would be a disaster to try to figure that out from this. So we want to do the nearest neighbor algorithm from the starting vertex, which is going to be home, which if we read the question up here, it says that the business, or Kim lives and owns a business in New York City. So I'm going to highlight New York City, and that's going to be our home vertex. That's where we're going to start from. So if we're doing the nearest neighbor algorithm, so nearest neighbor algorithm will say to start in New York. So we'll start in New York, and we will travel using the cheapest flight possible from New York. So you got to look at all of the edges coming off of New York, which there are 5 of, and find the cheapest one. Now the cheapest one here, using the graph and using the table, try to use one to do the problem and then try to use the other, because the table is also pretty useful. If you look at the list of flights coming out of New York, right, we can see a list of them. So it's kind of easier to find the cheapest one in the table if you think about it. This 98 is going to be the cheapest. So I'm going to say we're going to fly to Miami, and I'm going to add that on the graph as a flight used from New York to Miami. And then the nearest neighbor algorithm says go to Miami and now find the cheapest flight from Miami. We're not going to fly back to New York yet, obviously, but there are 4 options flying from Miami, and we just want to choose the cheapest one. And if you look at I guess it's harder to look at the table because we have to look at these. We had to look at these 4, but also this one, because that's also New York City. So maybe don't use the table. Let's look at the graph instead. So Miami, the cheapest flight from Miami, the cheapest of these 4 is it the 214? I think it's the 214, because they're 514, 214, 244, and 307 are the flights that are from Miami. So the 214, which goes to Houston. So let me highlight that flight there. We'll go from Miami to Houston as our next flight. And I guess we should keep track of how much they are here. 98. The next one was 214. And then from Houston, we're going to take the cheapest edge that we can find, not using any edges that we've already used, and also not returning to New York yet, right? We don't want to take this flight going back to New York, because then we would have closed our Hamiltonian circuit too early. So we're going to say this one, or this one, which means 305, 314, or 324. The cheapest one there is the 305 that takes us to Chicago. And then let me put that on here, the 305 that takes us to Chicago. And then from there, we only have a few options because we've only not visited Los Angeles and Seattle, right? So the only vertices that are left are Los Angeles and Seattle. So we're only going to consider those 2 edges going from Chicago. So the prices for those were 314 and 179. The 179 is obviously cheaper. So we'll go to Seattle next for 179. And then from there, we have to go to LA because that's the only vertex that we have not visited yet. So there is no option here from Seattle. We have to go to LAX before returning to New York City. So we have to go to LAX and then return to New York City, and the prices for those flights are $242 and $177. So we would add all of these up to give us a total weight or total cost in dollars. So go ahead and add those up. 98 plus 214 plus 305, 179, 242, 177 gives us 1215. Right, so this would be what the nearest neighbor algorithm produces. Now I'm gonna also do I know this question doesn't ask for it. Oh, I guess the next page is the same table. So you should cross off all of these. On the next page, you're gonna do the repetitive nearest neighbor algorithm. So now that we have the picture, you can kind of just continue on this page if you want to. But repetitive nearest neighbor says instead of starting at n, what happens if we start at all of the other vertices? So you'll do this process 5 more times. So instead of starting at n, we'll start at m, do the nearest neighbor algorithm. And then you'll do it again starting at l and getting different total costs, or maybe the same total cost for each one. And then finally boxing the cheapest option that you came up with. I'll let you do the repetitive nearest neighbor algorithm. But for the cheapest edge, I kind of want to help you with the cheapest edge as well. Let me copy this to the page down there. So we'll use this same graph without the highlighted edges, obviously, because we're going to make a new Hamiltonian circuit here, and we don't have a starting vertex. So with the cheapest edge algorithm, we will list the weights of the edges, all of them, which I guess we have a table for that, right? We don't have to necessarily, I guess we do have to list them, because we have to list them from cheapest to most expensive. So on the side here, I'll start listing these. If I make a mistake, please let me know. 98, 177, 179. Let me actually highlight these as I go. 179. And then in the 200s, the smallest is the 204, I think. And then the 214. Did I miss one? Oh, thank you. There is a 169, so let's put that right up here. Thank you for paying attention. 169 should be up there between the 177 and the 98. Hopefully I didn't miss any other ones. 214 and then I see a 242 and a 244. Those are the next cheapest ones, 242, 244. I guess we'll see when I'm done if I've missed any other ones. And then anything else in the 200s? No. In the 300s, we got the small ones are 305, 307. And then I see a 14 and a 319. 14, 319. And then 324, 336, and 514. I have a feeling we're never going to use that 514, but we need to include in the list just so we have all of them. Cool. Now that we have all of them listed, oh, I really didn't want to highlight all of these. Okay, well, let me oh my God. Okay, there we go. Got it. Finally. We will now start taking the cheapest edge and just adding it to our circuit. So we add the $98 flight. The next cheapest is the 169. Where is that? That's here. As long as S and N are both available, we can add that one. I don't see why we wouldn't be able to right now. So we add the 169. And as you're doing this, kind of keep track of what vertex is flown. Right now, N is done. Right? We can't add any more edges that use N because we already have 2 edges connected to it. So the next one in question is the 177, which is this flight here, and we cannot include that because N is no longer available. So this is not something we're going to add. The 179 in question on the next one is this edge here. That one is totally fine to add. So let's add that one. So the 179 we are using. The next one is the 204. The 204 uses N, which is not available, so no on the 204. Is the 214 available? Or is the 214 valid? The 214 is valid. That's this one here. Both of the vertices for the 214 were available, so 214 is good. But now notice that N is unavailable, S is unavailable, and M is also unavailable because all of those vertices have 2 edges that are connected to it that we've added to our circuit. Next is the 242. Where's the 242? That goes from S to L, so we can't use that one. The 244, where's the 244? That uses C to M, but M is not available, so that's not good. The 305, so 305 seems available, but if I included 305, this edge that connects C and H, we actually run into a different issue. We've now closed our loop without visiting L. Right, so 305 is also not a valid edge, even though the 2 vertices are available. And that's because you're not supposed to complete your circuit until you've visited every vertex. So next would be the 307, which is not available. The 314 is available. So the 314 is valid. We can go from C to L. And then at this point, it doesn't really make sense to keep going down the list of edges, but you can. You'll find that the 319 is not available. The 324 is the edge that we want to include to finally close our circuit now that we've visited every edge. Every vertex. And we can kind of just highlight these edges that we used so that we can add them together to get a total cost for our trip. And as far as writing the trip, you can start at any of these vertices and just travel along one way from there. So if I wanted to start at L, for example, I could just go L to H to M to N. I guess I'm running out of room here. To N to S to C back to L. Right, and the weights I've highlighted on the side over here. There's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And adding those together, we get 169 plus 179 plus 214 plus 314 plus 324. We get Interesting. Then we got a bigger one here. 98. Let me double check. 169, 79, 214, 314, 324. Yeah, we get a total cost, which is kind of an interesting result. Total cost of $12.98. So using the cheapest edge algorithm, this is the trip that we find for this total cost. Okay. We don't have a lot of time. I will let you work on the leftover problems, or I guess the leftover problem with the repetitive nearest neighbor algorithm.